This is one vertical line. I'll put a mirror here horizontally. Okay, that's your mirror. What will happen upon reflection? You will get this line below. Right? This is what will happen. Correct? Okay, that's something you know. Now, suppose I give you just this line again, but this time mirror I am not going to place horizontally. Mirror I am going to place at 45 degrees. Okay? Now tell me what you will get. Draw the curve. What are you going to get when you reflect in this mirror? What are you going to get? You understand, right? I have placed a mirror like this. That's the plane. So what do you get? You get this. Agreed? This is what you will see. Okay? What happened?
That is not a light beam, right?
No, that's just line. I have drawn a line.
It's an object kind of thing.
Yeah, you think of a stick here, a straight stick here. Okay? Then you have a mirror, and I am asking what do you see after reflection. So if you see after reflection, this is what you will get. Now, third one. Where is it? Now, let's go to this one. Take this one. This one. Now what I'll do is I'll put a mirror, which is a challenge, here at 45 degrees. 45 degrees to this vertical line. Okay. Now what you will get? Draw it. You will get this and back to that. This is good practice with mirrors now. This is what you are going to get, right? Agreed? Now, and see, this angle is 45 degrees. Okay? And when it reflects, this also is 45 degrees. That's why the entire angle between these two lines is 90 degrees. Okay? Similarly, this is 45 degrees. So this line gets reflected here and it makes 45 degrees with the mirror. And that is why this entire angle is 90 degrees. Okay? Now think of a line. So let's take a line here. What will happen to this when I reflect in this mirror? Let's say it makes an angle alpha from this axis. Okay, so x alpha. So you are going to get after reflection this thing. And this angle will be alpha. Agreed? If I take a curve like this here, it will reflect into a curve like this here. This is fine? That's all I wanted to tell you about mirrors. Do you remember how e power x looks like? Okay, this is x, this is y. And you remember how exponential function looks like? At x equal to 0, what is e to the x? 1. So this is 1, this is 1. This is 0, this is x, this is y, and I am plotting y equal to e to the x. Okay, something of that sort. So this is e to the x. Now, pay attention. This is y equal to e to the x, okay? Y is equal to e to the x. Given a value of x, pay attention. Given a value of x, I have a corresponding y here. Given a value of x, I have a corresponding y. So let me put arrow like this, which means this point is mapped to that point because of the exponential function. Okay? Now, what I'll do is, I will draw the same function, same exponential function again, but I'll just change the axis. I can do that, right? Who told you that x should be in this direction and y in this direction? I could have chosen x to be in this direction, y in this direction, and still plot the same function. That's what I'm going to do. I'm not going to do anything new. Now look at this. So if I get this correct, now this time I want to put y on this, x on this, and still plot e to the x, right? So this is minus x, this is minus y. Okay, that's minus y direction, that's y, this is minus x. I want to plot the same thing. So what is it? As you go from negative x to positive x values, your function, which is close to 0 far away, starts increasing and goes to larger values and starts rising as x increases, right? So here we'll do this. As x is very large negative number, you are there. So in that case I am here. I'm here, okay? At x equal to 0, y equal to 1. So at x equal to 0, y should be 1. This is y equal to 1. Right? That's the y-axis. Correct? Now see whether I am plotting the same thing. As I am increasing from negative values to positive values of x, today everything will go wrong. Agreed? Okay, very nice. This is nice. Now what it is saying is, given a value of x, that's the value of y. Given a value of x, that's the value of y. It's exactly the same plot. There's no difference. Right? This you agree? Okay. Now let's put it different way. I say, go here. Given a value of y, what's the value of x? That one. Right? See, normally you are thinking x is mapped onto y because of e to the x, right? Now how about this? Because the function is such that for a given value of y, I have a unique value of x. If I choose a value of y, then I get a unique value of x. Okay? So here, for a given value of y, I have a unique value of x. The same plot, there is no difference. Now what I will do is, so what is this? This is the plot x, y is equal to e to the x, right? Y is equal to e to the x. It's the same plot. Yeah, so x is equal to log y. Agreed? If y is equal to e to the x, I have told you what log function is. X is equal to log y. Right? So that x is equal to log of y. Same plot. But I just want to redraw this plot without changing anything. I will just change the names. So because I want to tell you log of x, right? But if you don't want to worry about that part, you can already see that's the graph of log function. Right? It's the same function I am drawing. I am not drawing anything else. It's the same function I am drawing. So if you treat y as independent variable and x as the dependent variable, that's the log function. Are you fine? So here, if I just change the name, instead of calling y as y and x as x, interchange the names. So let's interchange the names. Call x as y and y as x. Then here it will become x, here it will become y. And this expression will become y equal to log x. Okay? No problem? So shall I do it, or maybe I'll do it, okay? I'll just change the name. So if I change the name like I'm doing here, then this expression will become y is equal to log x, right? After changing the name. That's fine.
Yes.
So I'm just changing now names. I will call x as y, y is x. Then in that case, this plot which is of x equal to log y becomes y equal to log x. So I can just remove this and call it x. Okay, because I'm changing the names. This is y. That's the graph of y is equal to log x. Understand? Log of x does not have a different shape from e to the x. It's the same shape. Right? What did I do? I took this and just drew differently. I mean, change the x and y axis. It's the same shape. Right? Okay. That's good to know that it's the same shape. Now, if it is the same shape, then you might think about this. Let's go back. Let me draw e to the x also on the same graph. E to the x is here. Now look here. I'm drawing e to the x also on this graph. Okay, so this graph, I'm taking this one and putting here. Okay, that is e to the x. If I had drawn it nicely, it would have been e to the x. Okay, this value for y, pay attention, this value for y, whatever e to the x is, sorry, I forgot to change the name here, right? It was not y, it's x. See, I relabel, right? So it should be minus x. And this should be minus y. Fine? For whatever value of x here, e to the x is this much. And since this plot, it's exactly the same plot, remember I was drawing it that way, for that exact value of y, that's the value of this function. Right? So if I take this point and take this corresponding value, and when I'm drawing it this way, I was drawing the curve this way, right? So let's say from 0 it is at minus 5. So at minus 5, whatever the value is, it's here. I go minus 5 here, whatever the value is here. They are the same values. I go to minus 2. Minus 2, whatever value is here. Minus 2, whatever value is the same values. Right? Agreed? Which means it is a reflection of exponential curve in a mirror which is at 45 degrees to this coordinate system, which is giving you the log function. Are you following? Is this point clear? That's the log function. Okay. What is this line? What's the equation of that line at 45 degrees? As x grows, y grows, y equal to x. So for points on this line, y is growing linearly in x. If you look at the points on the exponential function, as you go to higher and higher values of x, exponential e to the x grows, but it's growing way faster than this is growing, right? But log function, even though it's growing way slower than y equal to x. Okay? So x grows faster than log x, or log x grows slower than x, and I am thinking of only positive values of x because log is only defined for positive values of x. Okay? So from the graph here itself you can see that x, okay, let's put it, log x, this function grows slower than x. Agreed? That's a useful thing to know. Okay, that you will have problems where this useful information will be very useful. Any questions so far? If you paid attention, then you might wonder what's so special about exponential function. I never used anything about exponential function in doing whatever I have done here. If instead of exponential function, it was some other function. See, what's the relation between exponential and log? They are inverses of each other, right? I think I forgot to emphasize that point, that's why you are not following. When I was saying that corresponding to this x, that y corresponds, and then corresponding to that y, this x corresponds. That's the inverse relation, right? If then when you ask, what is the, if I am given y, what's the x? That is through the inverse function, right? So x you obtain through the inverse function, correct? And that is why when we were doing this thing, this is the inverse function.
So for example, the graph of x square, root x, the graph of root x will be reflection.
Okay, so x square root x, it will be, and let's do that. Actually, that is what I have planned. That's what I have planned. So let's take another example. Let's take a function f of x is equal to x square. Okay, so what is this? This is square x. Take x and square it. Okay, so y is equal to x square. So what gives you x? Square root of y will give you x. Okay, so x is equal to square root of y. Okay, that's how inverse function is defined, right? If I give you x and I get y, then what you are asking is, if I give you y, what will give you that corresponding x? That corresponding x is given by taking square root of y. Okay, so square root is equal to inverse.
It should also have plus minus, right?
Let's take positive for now. Okay, let's worry only about positive. I don't want to worry, get caught with multi-valued functions. Let's look at only single valued. Inverse of square. Is that fine? Okay. If that is fine, then let's do what we did earlier. Let's plot I will plot only the x positive part, okay, not the negative part. Otherwise, it will not be invertible. You understand? For a given value of x, I will have a unique value of y. But for inverse, there will be a problem. For a given value of y, I will have this and that, both values of x. If I draw this curve, okay. So let me tell you again. See, if I take a value of x, then I get a unique value of y. That's the function. But when I'm looking at the inverse function, I will have a trouble, because for a given value of y, this and this both are the values of x. I don't want that. So I look only at this part. So I will remove that. Okay. Good. Now we do again the same thing. Again I draw the same curve, but I change the direction of where I draw x and where I draw y. I want y to be on this direction and x to be in this direction, right? And I still plot y equal to x square. So y is equal to x square. X is positive in this direction, x is negative in this direction, y is positive in this direction. So y equal to x square will be agreed? Okay, the same function. So this is y is equal to x square. So given a value of given a value of x, I get a value of y. Given a value of x, I get a value of y. Given a value of x, I get a value of y. But I can read it differently. That is where inverse is. I forgot to mention there. If I read it for a given value of y, what is the value of x? Then this is the square root function. Right? So again, x is equal to square root of y. X on this is square root of these values. Correct? If I take any value of y, then the point on the graph is this value. But that's square root of that value of y. Correct? Let's change the names again. Let's call x as y and y as x. If I do that, then x is equal to square root of y will read as y is equal to square root of x. But then I should change the names here. That is the graph of square root of x. It's the same shape. Agreed? Okay. If you agree to that, let's put y equal to x square also in this. Y equal to x square also on this. Very bad. Again bad.
Will there be that?
If this is y equal to x square, and if that is the inverse function, and this function you have obtained by this curve you have obtained by taking exactly that curve and putting it this way, okay, then whatever I told you earlier tells you that these are mirror images of each other, right? Where the mirror has to be put at 45 degrees. Is that fine?